Welcome back to The Explainer. Today, we're tackling a genuinely massive topic. But don't worry, we're going to do it without all the intimidating jargon or complex math. We're diving into Daniel Drescher's brilliant book, Blockchain Basics, a non-technical introduction in 25 steps. Drescher's whole goal here is to bridge that annoying gap between purely technical manuals and high-level economic theories. And my goal today? Well, I'm going to distill his incredible 25-step journey into an essential 8-minute explainer. We're going to break down exactly what this technology is, why we actually need it, and how it works under the hood. So, let's get into it.
To really wrap our heads around blockchain, we have to start right here. This is the ultimate problem the blockchain was built to solve. Seriously, if you strip away all the crazy hype, the confusing cryptography, all those buzzwords, you're left with this single, fundamental question. How do you get a bunch of independent computers spread all over the world to completely agree on something and actually trust each other when there's absolutely no central authority in charge? Okay, let's dive into our roadmap for today. First, we'll look at the problem of trust. Second, defining the blockchain. Third, building the data structure. Fourth, achieving distributed consensus. And finally, limitations and smart contracts. Starting off with Section 1, the problem of trust, or why herding independent computers is just so incredibly hard. See, when you don't have a central server or a big bank acting as a referee, herding independent computers into a reliable network becomes a huge headache. In computer science, they actually call this the Byzantine general problem. Achieving system integrity when conditions are perfect, yeah, that's easy. But blockchain was designed to solve this under the absolute worst conditions. A purely distributed system where you don't even know how many peers are connected and you have literally no idea if they're reliable. It's kind of like trying to get 100 random strangers on the internet to perfectly agree on a complex lunch order without anyone actually being in charge. And when you're dealing with a system managing ownership, like a digital currency, failing to solve this problem leads straight to what's known as the double spending dilemma. Think about it for a second. Digital files are incredibly easy to copy, right? That's what they do. So if I have a digital coin, what's stopping me from sending a copy to you and then sending another exact copy to someone else? Without a central bank to verify my account balance, double spending just ruins the integrity of the whole system. A brand new technological solution was absolutely crucial here. Moving right along to Section 2, defining the blockchain. Let's disambiguate this massive buzzword. Before we look at how the technology actually solves that double spending issue, we need to clearly define what we're even talking about. The word blockchain gets thrown around a lot, but it's actually used in 4 distinct ways. First, it's a data structure, literally organizing data into chained blocks. Second, it's an algorithm, a specific set of rules for negotiating that information. Third, it's a suite of technologies that combines that structure, algorithm, and cryptography. And finally, it's used as an umbrella term for the entire distributed peer-to-peer system. The crucial takeaway here is that it isn't just one single thing. It's a whole suite of tools working perfectly together. Section 3, building the data structure. These are the literal building blocks of trust. So how do we store data securely in a system where literally anyone can participate? Now, what's really interesting about this concept is the comparison between digital data and human fingerprints. The blockchain uses something called cryptographic hash functions. You can basically think of a hash value as a unique digital fingerprint for a highly specific piece of data. If you change even a single comma in a massive digital document, its digital fingerprint changes completely. It makes any tampering instantly obvious to everyone. And these digital fingerprints are used to chain blocks of data together. Imagine a traditional library card catalog. Each card represents a block of transactions, and it contains a unique reference number that points back to the exact fingerprint of the previous card. By chaining them together with these hash references, the system preserves the exact chronological order of every transaction. Because each block relies on the fingerprint of the one right before it, any sneaky retroactive manipulation instantly breaks the chain and sticks out like a sore thumb. All right, Section 4, achieving distributed consensus. This is the machine actually at work. Okay, so we have this immutable data structure. But how do we get thousands of untrustworthy computers to perfectly agree on this shared library catalog without a central boss pulling the strings? Well, the answer is a brilliant incentive structure. Drescher compares it to managing contractors with a carrot and a stick. The algorithm forces all the computers, which we call nodes, into this constant working rhythm. First, they evaluate new blocks submitted by their peers. Second, they act as supervisors, catching errors or invalid transactions. And third, They fiercely compete to be the one to create the next valid block, because doing so earns them compensation, a nice digital reward. This creates a rhythmic, self-sustaining heartbeat for the whole network, where honesty is literally the most profitable strategy. But wait, what happens if there's a network delay and two different versions of the truth emerge at the exact same time? Drescher explains that the blockchain resolves these conflicts by letting computers vote with their feet. The network is hard-coded to always trust the longest chain, meaning it accepts the version of history that required the most aggregated computational effort to build. It's just an incredibly elegant mathematical way to reach democratic agreement. And this brilliantly illustrates how we should mentally separate the system into layers. Down at the bottom, you have the purely distributed peer-to-peer architecture. Above that is the implementation layer, housing the technology suite, the storage logic, the consensus algorithm, the cryptography. And finally, sitting right on top is the application layer, the specific rules for managing ownership and processing transactions. Stacking them like this creates a secure, highly available, and wildly resilient architecture. Finally, Section 5, Limitations and Smart Contracts. We are moving way beyond the basics here. Look, no perfect machine is without its limitations, right? Open public blockchains are incredibly secure, for sure, but they can be slow and computationally expensive. To get around this, businesses have created a taxonomy of 4 distinct blockchain variations. A system can be public or private based on who is actually allowed to read the data, and it can be permissionless or permissioned based on who is authorized to write new transactions. By restricting access, these private, permissioned blockchains trade away total decentralization for massive gains in speed and corporate privacy. And that evolution has unlocked what is easily the most exciting development in this entire space: smart contracts. By adding executable code directly into the blockchain data structure, we've moved from simply tracking who owns a digital coin to automating really complex real-world agreements. These are self-contained computer programs executing right there on the blockchain. They can automate paying your rent, settling complex bets, or even issuing a loan. It completely transforms the network from a simple data store into a massive, distributed virtual machine. It really is a remarkable journey when you step back and look at it. We started with the Byzantine general problem, just trying to figure out how untrustworthy computers can simply agree on a list of transactions, and we've arrived at a technology that can independently automate and enforce the contracts that practically run our society. It naturally forces us to ask, will these immutable, self-executing smart contracts eventually replace the traditional human ways we enforce our laws and agreements? That is a truly profound thought to leave you with today. If you enjoyed this, subscribe to In 8 Minutes and never miss what matters.